short, probably about 30 minutes, so I might go a little bit fast. I know people have different backgrounds. To some people this might be simple and trivial, other people will be like, oh my god, what the hell is that? So I think what I'm going to try to do is just get through it. And if you have questions, maybe just hold the questions, and at the end we can talk about them, or we can talk about them offline at the end of the meeting, because I know that other people have things to do. But the mission was to talk about Ohm's law, and this relationship of V equal IR is pretty fundamental to electronics. And he was not the only man researching that, but his name is associated with it now, so he gets credit. What I wanted to show here was V equals IR can be rearranged very easily, very advanced algebra. But the point of the slide is to say that sometimes you want to talk about voltages, sometimes currents, and sometimes resistances. So depending on what you want to do, what type of circuit you're talking about, you have to change gears. So this is a very beautiful relationship that does lots of good stuff. So before we get started, let's talk a little bit about what some of these terms mean. V, or voltage, the unit is volts, is a potential difference. It is an electromotive force that says if there is an electric field expressed between two areas of differing charges, there will be a force to get the charge to move from the area of greatest concentration to lesser concentration. Usually we're talking about electrons, but in semiconductors you can talk about holes and other charge carriers. For today, we're just talking electrons. The key, though, is that it's a potential difference. There is no such thing as an absolute potential. There is no potential in a vacuum. Everything is the potential of this with reference to that. It's a difference, A minus B. And the most important thing about that is what is ground, because usually people measure voltages with respect to a ground. And one of my EMC mentors, I guess, had this quote. He said, ground is for potatoes and carrots, meaning what the heck is ground? That just doesn't, it's such a nebulous term. It means so many different things to different people. The key is the reference. You are looking at a charged area with respect to or reference to a different area. So you have to define what that area is. These symbols on the right are just common ground symbols. The idea of having different symbols is to kind of provide logical partitions of what you're referencing. So these three right there usually mean digital reference to the left, an earth reference in the middle, meaning maybe an iron pipe that comes out of the ground, and an analog reference on the right. There's no magic about these symbols. They're just a way of kind of categorizing or sorting what you're referring a voltage to. The next term in there is I for currents, measured in amps. It's another famous gentleman, Mr. Ampere. An amp, by definition, is 6.24 times 10 to the 18 charge carriers passing a point in a second. That's a little bit bigger than our national deficit, but it's closing. The idea with an amp is current always flows in a loop. So at any point in the loop, you can pick an arbitrary point, and if you measure how many charge carriers go past that point in a particular amount of time, that is the current. And that is analogous to a flow volume. It's like the difference between water that comes out of a straw versus water that comes out of a fire truck. It's still water, but it's just a volume per time. Resistance, the third of the V equal IR, is kind of a derived characteristic. It's a ratio between voltage and current. The neat thing about the idea of resistance is it applies to everything. Any type of circuit, at DC, at high frequency, anything you can imagine, that relationship holds. And that's kind of the magic of this equation. The two different types of resistance or resistance-like, there's resistance and there's impedance. Both are measured in ohms. Both are the ratio of voltage to current. But impedance actually is a superset of resistance. If you have objects that you can have, we'll talk about this in a little bit, can do different things. If the object only is capable of dissipating energy, like a resistor, then impedance simplifies to resistance, because impedance is the resistance plus Jx, where x is the reactance. Jx is a representation of energy storage. It's just a mathematical way of saying this device, in addition to dissipating energy, can also store energy. So we'll see that in a little bit. And then finally, P for power in watts, another famous guy, did steam engines. Watts is another universal field because watts, as a measure of power, applies to all kinds of things. Mechanical systems, electrical systems, all kinds of things. The neat thing about power is defined as the voltage times the current. But the voltage itself is the current times the resistance. So power can be rewritten as the current squared times the resistance. And finally, this is just for mechanical guys. 746 electrical watts equals 1 horsepower. So if you're doing motors, motors typically are quoted in horsepower. This is the conversion factor. So with that, you guys are now experts, and I'm going to go home. So building blocks. We're going to make a circuit. And there's different building blocks we can have, like different colored Legos. The two primary categories are passives and actives. The difference being that a passive is a device that you cannot change the current capability or the current handling or the current manipulation within a passive device. Whereas with an active device, you can actually change the current. You can amplify the current, attenuate the current. These are generally more complex devices, so they're things like tubes, transistors, SCRs, triacs, etc. But all devices, and I think this is right, would fall into one of two categories. Now the interesting thing is LEDs sit on the fence because LEDs are a semiconductor. But they fit the definition of passive because their behavior is well defined and there's no way to fundamentally change the behavior of a diode with, well,
And store energy in diode.
Well, you can store energy in diode, that's a different topic. But just bear with me, bear with the definition. Basically the fact is that with an active device, usually you're concentrating on the current through it, and I'll give you an example, an amplifier for example. Typically with an amplifier you might have a small current going through it. You extract energy from a power supply and then amplify the current. There's no such capability to manipulate or change the current of a diode. A diode has a fixed profile, which we'll see in a little bit, and so it simply responds to the stimulus you provide to it. So hold that off, I'll do a better definition with the diode later. So what we're going to talk about, let me back up. We're going to talk today about passives. The big three are resistors, capacitors, and inductors. Pretty much any circuit you can imagine can be described as a combination of those three things, short of semiconductors and the active category that's different. So today we're going to talk about resistors, capacitors, inductors, and we'll mention LEDs, because one of the questions I always get is, how the heck do you choose the value for the resistor to limit current for an LED? So we'll cover that. All right, so starting with the resistor. Resistor has no capability to store energy. It simply is a dissipator. The best example of a resistor is probably an incandescent light bulb. It has a tungsten filament that when current goes through the tungsten impedes or resists the flow of electricity, and in the process heats up. So it converts electrical energy to mechanical energy, i.e. kinetic energy, and gets very hot. It also converts the electrical energy to electromagnetic energy and radiates light. But in the words of a smarter man than me, an incandescent light bulb is actually a space heater that coincidentally gives out a little bit of light. But so here's the resistor. The next thing, this is actually the first application of Ohm's law in this presentation. Ohm's law, like I said, is V equals IR. So if I tell you that's an incandescent light bulb, it's 120 volt AC in the wall, it's a 60 watt light bulb, you have all the information you need. Using V equals IR, you can calculate either or both of the current that goes through it and its resistance. And we'll see that a little bit more. We'll look at actual circuits. So multiple resistors. This comes into play in a couple different categories. One, you may be building a circuit, you need a resistor of a certain value, but you don't have it on shelf. So you can manufacture your own resistors. There's two ways you can do it. If you wire resistors in series, they add. So the two 10K resistors, they are wired in series, end up being functionally equivalent to a 20K resistor. Now there's a limit to this statement that at very high frequency, the interplay between the two resistors actually changes slightly, but for the purpose of the discussion with ideal resistors, you can simply add resistors by putting them in series. Likewise, if I put resistors in parallel, I diminish them because I add them by their reciprocal. So these two relationships are fundamental both to synthesize new values and to analyze circuits. And you will see these repeat for both the inductor and the capacitor in a minute. So now we'll talk about capacitors. Capacitors and inductors are different than resistors because they have an additional capability. They can store energy. A capacitor stores energy in the form of charge. So what is a capacitor? A capacitor simply is two conducting plates placed close together. Between the two plates is something called a dielectric. So what happens in this situation, I probably should have drawn this. If I place a battery across the two leads, such that the positive lead is here and the negative lead is here, the battery will deposit positive charge here, And also at the same time, because of the attraction of opposite charges, negative charges will be pulled off the battery to balance on the other plate. So one plate will become positive, one plate will become negative. Because there's a difference in charge, there's now a potential difference. There's a voltage impressed across the capacitor because it's storing charge. The dielectric here is sort of the secret sauce of the capacitor, because I can make a capacitor pretty simply with any conductors. I can take 2 pieces of aluminum, 2 pieces of iron, 2 pieces of copper. But the dielectric is critical because the dielectric determines how much charge can be stored in that capacitor for a given voltage. And it determines things like how much voltage can be impressed upon the capacitor before it destroys itself. It also gives some RF characteristics, which we won't go into tonight. But the important thing about capacitors is they are voltage controlled. They are devices that you primarily think of in terms of voltage. They store charge, and their secret formula, the value, the IP, if you will, is dielectric. So if I go to the store and want to buy a capacitor, these are some of the things that I look at. I look at things like, what's its value? Values are measured in farads. I can buy a microfarad, a millifarad, multiple farads. What's its voltage rating? That means how large a voltage can I impress across it before it self-destroys itself, before it commits hara-kiri. What package does it come in? These can be pin through hole, and I've got examples here after the meeting to show. They can be axial capacitors, like these are sort of drawn. They can be radial capacitors, 2 leads out the same direction. They can be surface mount. And the neat thing about surface mount is the designation for the surface mount package also gives you the physical size. If I look at a 402, for example, that actually specifies a rectangle that's 40 thousandths of an inch by 20 thousandths of an inch. A 603 is 60 by 30. So it's kind of nice because you can look at the package name and know how big the part is. Whereas if I told you it's radial or axial or ceramic disc, you don't necessarily know. So that's a capacitor. The other thing I'll point out is there's a couple different ways to represent them. This one on the left is non-polarized. What that means is there is no preference between the 2 plates as to which is the higher potential. So I could connect this as the most positive or this as the most positive, and it's perfectly fine. The other 2 are polarized, meaning the lead or the plate on the top in the drawing has to be a higher potential than the lower plate. Otherwise, you risk damaging the part. Now, what does that mean? Well, if you're using a DC application where this side is always higher than this, it doesn't matter. You can use the parts interchangeably. However, if your signal is strictly AC, meaning it's actually swinging from a plus voltage to a minus voltage, there is a time during the swing that the potential difference across the capacitor will invert, it will switch. And polarized capacitors are not very happy doing that. Now there are ways around that. You can team polarized caps together to get around that. But it is important to understand when buying a cap if it's polarized or non-polarized, and if it's polarized, which side is the higher potential. So multiple capacitors. This is just like resistors, but in reverse. This says if I add capacitors in series, the upper picture, then the resulting capacitance is reduced because series capacitors are added as reciprocals. If I put capacitors in parallel in the bottom, they add as just 1 plus 1. They add, well, C3 is C1 plus C2. So this is the reverse of the resistors. Now what you'll see in a minute, or the third thing is inductors. The inductors follow the path of resistors. So you either have a resistor or an inductor, and they diminish in parallel and add in series, or you have a capacitor, which is the opposite. Okay. And finally, the inductors I alluded to. The inductor, like the capacitor, is kind of it's like the other side of the coin. Inductors store energy as well, but they don't store it as charge, they store it as magnetic fields. And the way this works typically is the number 1 rule you learn in engineering is the right-hand rule. The right-hand rule is, if I hold my right thumb up and current is flowing in this direction, there is an enveloping magnetic field spinning in this direction. Well, if I want to maximize that effect, I take my piece of wire and I curl it like a spring or like on a bobbin. And doing that, as the current is flowing around the bobbin, the field is naturally accumulated in the center and magnified. It's concentrated in the center of this winding. That is how the energy is stored. Now, like the capacitor, there's several different parameters that you would use to buy one. You buy the value in henries, milli, micro, whatever you want. Current rating here is the critical as opposed to a voltage rating for a capacitor, because with an inductor, the amount of current that can go through it is limited by how much magnetic flux you can get inside the inductor. So they don't have infinite current. And where this comes into play is if you're using an inductor, for example, at the output of a switching power supply. That's one of the things people get trapped in, is they may be building a power supply that's capable of 5 amp delivery, but the inductor is only a 1 amp inductor, so it's kind of like throttles the power supply basically. So the key takeaway from this slide is inductors are a function of current. The entire effect is one based on current, and they ultimately are limited or described by how much current they can deliver. The other's pretty obvious. They come in different packages, just like capacitors and resistors. With an inductor, the secret sauce is the core. That is, if I've got my bobbin or my wrap of wire, inside that is the core. It might be an air core, it might be an iron core, it might be a rare earth metal, it could be lots of different things. But the secret sauce of an inductor is, it's a couple things, but one of them is the core, because the core determines how well the inductor can concentrate the magnetic flux, and therefore what value of inductance you get and how much current it can carry. And then this is my comment before. In terms of adding these in series or parallel, think of them as resistors, if I was lazy and didn't bother redrawing the diagram. Okay, so now we'll actually get to, let's actually do something with this V equals IR. This is a resistive circuit. There are 6 resistors there. If I were to show you this diagram in the very top right and said, so tell me what IS, I1, and I2 are. It's not obvious just looking at that what the currents are. So the way you attack that is to use the rules I just talked about. You take those 6 resistors and basically condense them or distill them into one equivalent resistor. And the way you do that is you simply walk around the path of the loop, because current always flows in loops, and you see, I should have a pointer, I guess, but what is this? If I'm IS, I travel through the path, I see a 20 ohm, then a 50 ohm, then a parallel combination of 2 legs. One leg is 70 and 20, the other's 40 and 20. So what I have to do is mathematically combine all these resistors into a single resistor to make my life easier. So I start here, and here's the math. It's 20 plus 50 plus the parallel combination of 40 plus 20 and 70 plus 20. Obviously the addition's trivial. The parallel combination, since these are resistors, uses the reciprocal relationship. So it's 1 over the first resistor plus 1 over the second resistor, inverted. So you do the math, do the algebra, you end up 20 and 50 carry, and this combination of 4 resistors, these 2 parallel legs, ends up being 36 ohms. So adding those up, I get 106 ohms. Now what the heck does that tell me? Well, I know I've got a 120 volt supply. Across a 106 ohm resistor, what's my current? V equals IR. So I determined that the current is 1.3 amps. So now I know in the base circuit over here, this IS is 1.13 amps. The only other thing I have to determine is the current, as it comes up to the top part of the loop here, is divided between the 2 different legs. So how does that work? How do I figure out what's going on? Well, I set up the relationships that I know. I know that IS has to equal the sum of I1 and I2. Otherwise, current's flying off into the universe and is being simultaneously destroyed, which physicists would shoot me for. So I know the sum. I just have to figure out one of them.
Would an electron come?
Well, energy can be propagated by electromagnetic wave. Well, anyhow. So I know the sum is 1.13 amps. I know that the potential difference, and I'm measuring from A to B, so that means the potential of A minus the potential of B, is the same for both of these legs because they're in parallel. So I just set up my relationships, and I say that 60 ohms times I1 is the potential V equals IR of AB. It's also equal to I2 times 90, the other side of the leg. So doing a little bit of algebra, and I won't bore you with the details, you end up that I2 is 452 milliamps and I1 is 678 milliamps. So this is how you solve a basic passive equation. If you want to know to solve a circuit, what you need to know are, at any node of interest, I need to know a potential. I need to know a potential relative to a reference, and here I've designated it here as the lower side of that power supply. And I need to know the current through any leg of interest. So I've completely solved this circuit. Now, this is not to say this is the only way to do it, certainly. You can attack it from different directions, however you want to do the math. But this is kind of a good outline that shows the final answer, what do you want it to be. Now, this is a double check. One of the double checks is if I add these two numbers, they equal that. Okay, so maybe I didn't screw that up. The second thing to do is, if I want to know what the output voltage is, at any given time, at any point in the circuit, all I have to have is a resistance and a current going through it, and I have a voltage. So I can subdivide, if I wanted to, I could break these resistors into pieces and reorganize them, whatever. But V equals IR. Okay, so now we get to capacitors. Capacitors are much more involved. They have an ideal capacitor, has one role, and that's to store charge. Now, are there ideal capacitors? Absolutely not, because a real capacitor is made of leads of metal, therefore it has resistance. Secondly, a real capacitor has dielectric in the middle. Dielectric, except even the most expensive dielectrics, dielectrics have charged particles. They have dipoles embedded in the dielectric. So when the voltage is changing outside the capacitor, these little dipoles inside the dielectric are moving, so that results in loss. Anytime you move matter, you have to exert energy. So there is no such thing as a real capacitor that is only capacitive. But for this purpose, it exists today. So when we look at a circuit that has a reactive element, i.e. an energy storing element, there's a couple different ways to look at it. One of the first ways to look at it is as a transient. And the transient response says, this little guy at time 0 has no charge on it, therefore its voltage is 0. And I turn this 10-volt DC power supply on. So what happened to it? Well, I didn't want to go into all the math, but there's two curves that are being traced simultaneously. This is the voltage, this is the current. To give you a little bit of the math, the current through a capacitor is C dV dt. In other words, the capacitive value times the first derivative of the voltage. I just created a large derivative because I just turned this thing on. It went from 0 to 10. So the amount of current instantaneously is very large. In a perfect world where if there were no resistance and this was a perfect power supply capable of a gazillion amps, this current through the capacitor would be infinite. It would be way up here. But the max current is limited by the resistor. So the current starts out as a max, and as the capacitor charges, the voltage across it increases. Taking the potential difference from 10 volts to the top of the capacitor begins to diminish. A diminishing potential difference across a fixed resistor means a diminishing current. So the current has to diminish. Eventually, this guy charges to the full voltage. The potential difference across the resistor is 0. The current is 0. So that explains what the current is doing. But what is the voltage doing? I turn this on instantaneously because it's a magic power supply that's perfect. I would expect the voltage for the output to go from 0 to 10 volts or to some value instantaneously. Well, obviously it doesn't do that. If you've ever looked at clock traces on a board, maybe clocks going into an IC, you notice that instead of the nice perfect vertical rise in the pulse and then continuation, there's this nice rounded rising edge, which is this effect right here. And that is just because this power supply, because it's limited, driving through a resistor, cannot provide infinite current to charge the capacitor instantaneously. It takes time to charge the output voltage. So how do I quantify that output voltage? Well, there's a kind of a standard rule of thumb called a time constant. The time constant is the resistance times the capacitance. So it's 1K times 1 microfarad in this case. That's 1 millisecond. The time constant says this is kind of a rule of thumb since this curve is obviously nonlinear. I want just a simple algebraic relationship that kind of gives me an idea of how long it takes for this voltage to go up to the rail. So these are just kind of rules of thumb as you're waiting. So if I wait 7/10 of a time constant, which is 0.7 milliseconds in the example, I expect the rail to go about halfway, to go right there. If I continue to wait a full time constant, I expect the rail to go to about 63%. And finally, if I wait 5 time constants, I'm pretty much assured that I'm out here somewhere. So the output is totally charged. Now, there's a couple interesting things that go along with these curves. Number one, V out never obtains this voltage right here, because there's a, well, I'm sorry, excuse me, I'm thinking ahead to the next example. Never mind. It does charge the rail. So it goes all the way up to the rail, because eventually the current falls to 0 when this guy is fully charged. So in this diagram, I think the other thing I wanted to show was the current here goes to its maximum value before the voltage does. That's important in an AC circuit. What that means is, you ever hear the term that says the current leads the voltage or the voltage lags the current? What that's saying is, when we get to a steady state circuit, which we will to in a minute, that the voltage and the current are no longer in phase because of this storage capacity and the finite time required to charge it. If I were to look at a voltage across a resistor, just a resistor, the current through a resistor is always in phase with the voltage. It's just a scaled version of the voltage. But here there's actually a phase difference. So, go to the next one. So, I take a slight diversion. I mentioned impedance before. At this point I want to talk a little bit more about impedance. There's two perpendicular directions or dimensions to this graph. One, the horizontal is resistance. The vertical is reactance, it's storage. There's only two types of storage. You can either be inductive, you're storing magnetically, or you're storing charge. So what you can do in any given circuit, and get back. If I go back to this circuit, if I look at what the overall impedance is, I have an R and I have a C. So if I go to this equation, obviously the previous circuit was capacitance. The reactive portion is negative. That's the definition of being capacitive. So the impedance of the previous circuit looks something like this. This diagram gives me a couple good things. One, tells me what the real part is, so if I'm a power guy and I'm distributing AC, I know how much of the energy is actually being dissipated as work. But two, it also gives me a phase angle, which is the angle between these guys, which tells me if I've got a sinusoidal voltage and a sinusoidal current, how much difference in phase will there be? That is equal to this angle right here. And the final thing about this graph is there is a magic part of the graph. If you were just on this line right here, that's just resistance, that also correlates to something called resonance. Resonance means that in a circuit, any part of positive inductive reactance is essentially canceled by an equal amount of a negative capacitive reactance. Resonance is important in circuits where you want to minimize the impedance. You want to remove this phase shift, and you want the current to be back in phase with the voltage. So I won't talk about that too much, but I'm just trying to introduce the concept of impedance. And if you look here, these are the equations, if you will, of impedance for the three devices. So a resistor has no storage, so this part of it is 0, it's only R. These guys have reactance. The reactance for a capacitor is 1 over j omega c. The reactance for an inductor is j omega L. So they are reciprocals of each other. And the sign changes. But also, perhaps more importantly, is in the j omega c, omega is 2 pi f. So the reactance and thus the impedance of both of these guys is frequency dependent. And that's kind of what makes capacitors and inductors interesting. That's why you use them for filters. But it also makes them a little bit more complex to understand than just a resistor. A resistor is a much simpler guy. And finally, my comments before, the top half of this plane is inductance. The reactance is positive. The voltage for any circuit that has an impedance that looks like this, the voltage leads the current or the current lags the voltage. These are equivalent statements. Likewise, the bottom half plane is negative reactance, therefore capacitance. Voltage lags the current and current leads the voltage. And we've seen in the previous diagram that with a capacitive circuit, that indeed the current leads the voltage. And finally, resonance is if I have a circuit where I have an inductive element and a capacitive element at a particular frequency, they cancel each other out. And it can be, well, that's as much as I'll say about that. I guess we can talk about that later if you want to. So going forward, capacitive circuit. This is the same circuit as before, but now, instead of a transient where I just turn the power supply on and wait, I'm actually driving this with an alternating voltage. So I've got a 10 volt, 60 hertz signal, just like what comes out of the wall. And as you'd expect, the output here is a sinusoidal output because the input is sinusoidal. That makes sense. The current is also sinusoidal because the voltage across a fixed resistor is sinusoidal. So there's no reason to expect that they wouldn't follow each other in terms of shape, but they don't line up. As you can see, the current leads the voltage. And I didn't do that in this slide, but if you actually measure, if you go back here, since it's capacitive, this phasor, its movement is dependent on how much resistance there is. If there were no resistance, the phasor would be pointing straight down, and the phase angle would be minus 90 degrees. Since there is resistance, this phasor is moving, so the angle changes, and I didn't bother to calculate it, so leave it as a homework problem. I can't tell you exactly what the phase difference is between here and here. If there were no resistance, it would be 90 degrees, but it's less than 90 degrees. Otherwise, once I know it's capacitive, and I've addressed the issue that there's a phase difference, it starts to look again like a resistive problem. That is, if I forget about the phase for just a minute, I look at the impedance of this capacitor, I take its magnitude, which, since it's a phasor, you get the magnitude of a phasor, it's just each component squared, summed, and then square root. So if I forget about phase, I take the magnitude. I can now treat this capacitor at a certain frequency as a resistor, 2600 ohms basically. And all I did was use this magic equation, which is the impedance of a capacitor, which is minus 1 over j omega c. So at 60 hertz, it ends up being 2600 ohms. And then it's exactly like any other problem. I've got a voltage, a resistor, and an impedance, but at a particular frequency it's fixed at 2600 ohms. So I can solve that equation just like I did before, and I can say, okay, what is IS? Well, IS, a current, is a voltage divided by a resistance. So the total resistance here is 3600 ohms into 10 volts is 2.74 milliamps. I can do the same thing for the output voltage. So in this type of circuit where the frequency is fixed, as long as you understand that it's not exactly a resistor because it does have phase, at a particular frequency it sort of acts like a resistor. If I change the frequency, if I made this 100 hertz, 1000 hertz, a megahertz, then the impedance changes. This phasor that I showed you in the previous diagram moves, and the phase between the two changes. And actually I guess also the magnitude changes too, because the magnitude is here. But if you're looking at this type of analysis, you're saying at a particular frequency, in this case 60 hertz, what does it look like? Okay. Let's see what it looks at. And now the famous one, I guess I'll end with this, okay, is the LED. LEDs are awesome. Okay, I'm a double E, I'm a geek. I love LEDs, I admit it freely. An LED is just a diode. What is a diode? Well, as it turns out, all diodes emit light. It's just that certain diodes are built in a way to emphasize that capability. So they're called light-emitting diodes. Well, a diode is a semiconductor. It means it's doped material. It means it has two pieces. The one side of it is positively doped, is called an anode. The other one is called a cathode. And the way I remember that is this looks like a catheter. Not that I've ever actually had the use of one, thank goodness. But the way a diode works is there's something called an IV curve. This is current as a function of voltage. This is the fundamental relationship that explains all diodes, including LEDs. The way this works is if I apply a potential difference across the diode of just a very small amount, I'm here on the curve, nothing happens. Because I haven't given enough force to have current jump across the barrier or the gap between the positive material and the negative material. So I'm just cruising right here. Well, if I continue to increase the voltage higher and higher, eventually I get over the gap. And my curve starts to go up. This is the knee right here. The knee says that if I'm at this point, I'm kind of on a teeter. Because if the voltage decreases, I go back here and I'm dark. If the voltage increases, then I go up here. And now you see my current, which is the Y dimension, goes up astronomically. So the danger with a diode is, if you continue to forward bias a diode, eventually you will end up on this part of the curve and you'll destroy the diode because there will be an avalanche of current through it so much that it will heat up and destroy itself. So the key is, okay, I need to limit current. How do I do that? Well, a very easy way to limit current is a resistance or a resistor. So the question is, how do I choose the value of the resistor? Well, I really want to keep the diode here or somewhere close by. So the two parameters I need are forward voltage and a forward current. I don't know if you guys can see that. It doesn't come across very well. But
VF, IF.
yes. These two parameters vary based on the type of diode you buy, based on the chemistry of the diode, based on how many diode elements are in the package. So it's hard to say this is exactly this and this. So the key is you got to look at the data sheet for the diode. You get these two values. Then this is V equals IR. I got a voltage, I got a resistor. All I need to know is I set my current for my evaluation to be IF. I set the voltage that I'm pressing right here, V out, as VF. And I did math. The math says 10, which is the source voltage, minus the VF over an R is a current. And I do a little algebraic manipulation. I get the resistor value, 10 minus VF divided by IF. I know these two, so I calculate R. The other thing that's interesting about this is this knee, or this IV curve, applies, like I said, to all diodes. And there are lots and lots and lots of different types of diodes. There's another type of diode called Zener diode. And the Zener diode is made in such a way that it actually lives out here. It expects to be driven at the negative side of the thing. And the reason why is it becomes a shunt. It's used in voltage regulation where you want to protect against over voltage. So this guy, if you start to drive him too hard, I mean, it really slams quickly and prevents whatever's attached to that point from seeing an over voltage. So it's just another feature of a diode that gets used. And I guess that's all I have. That's V equals IR and solving simple circuits in about 30 minutes. So I will shut up now and, okay, do we have, what's our schedule like? Do we have time? Or?
We're golden.
Okay. Go ahead.
Okay, back in the dark ages when I went to school for this stuff, I was taught that inductors have reactance and capacitors have reluctance.
Okay.
You're calling it positive and negative reactance. So where justifies the wrong word, but explain that to me.
I think it's just nomenclature.
Really?
I think it depends on who you talk to. Different subsets in engineering have different sets of things. Like we talk to an RF guy, he likes to talk about they talk about Siemens and ohms and mhos, and it's just a different vernacular. I think functionally we're talking about the same thing.
Yeah. Well, I think we are, but
I can't tell you why though.
I've never seen positive and negative reactance. I've just seen reactance and reluctance.
I learned it as positive and negative.
Okay.
You learned it positive and negative?
Yeah, Carl, they also don't talk a lot about triodes and grid voltages anymore.
Condensers.
Well, like I said, I did this in the dark ages, you know. It was the 1970s when I went to school. So.
Chip's first.
Oh,
Jim in the green shirt.
sorry. So if I did a parametric search for capacitors, and you had mentioned the cool thing about those SMD components is it tells you the size, right? The 06, 03, 08, 05. There's two capacitors that have the same characteristics in terms of, you know, capacitance and, you know, breakdown voltage and all that. But one was 06, 03 and one was 08, 05. Is there any difference in using those two in a circuit?
It can be. It's
Other than size?
generally on a larger package, there's more space, so they're able to do better packaging things. So they can actually orient at a physical level. They can create a capacitor that has lower parasitics. So if you can tolerate the space and everything else being equal, then usually it's a good idea to use the bigger package.
What are parasitics?
Parasitics? Okay. We talked before. Let me go back to the last issue.
At the internal resistance?
Yes.
Well, we're talking tonight about ideal things. So an ideal capacitor is only a capacitor. That's all it does. But that's not really real. I take this capacitor and I mount it on a board. So I've got, can I draw on the board? I take an 805 capacitor. Okay, looks like that. Well, I can't just throw it on the board and expect it to work. Obviously, I've got to connect it. So it's got to come off with leads. There's probably vias here. The vias, depending on what the capacitor is doing, the vias may be tied to reference layers that are inside the board. They may go off somewhere else to a signal. The point is that this capacitor, as soon as you use it, becomes more than just a capacitor because there are parasitics. There's inductance and leads here. There is capacitance. If the traces are long, there's probably a tiny bit of capacitance from the trace to the reference layer underneath it. There are parasitics inside the package itself because there's some material, some ceramic material inside the package, but it's got to get out to a little piece of metal on the end and then out to the board. So anywhere there's a discontinuity where the material changes, like a pothole in the road, there will be additional reactive elements. There can be inductors and capacitors. Not like we're talking ideal, but there can be the current flowing through the trace sees what it thinks is capacitance or inductance. So if you're really going to do a full circuit analysis of this device that we call a capacitor, it gets to be fairly complex. It actually looks like the capacitor. Well, I don't want to do the whole thing from memory, but it kind of looks like, you think about it as a capacitor, but there's parasitics in here, there's a little bitty resistor in here. These guys have some resistance. You can pick up inductance here because you have to think about how the current is flowing between this element and what's supplying the power to it inside the board. So it's fairly complex. If you actually were to look at what this thing looks like, if you were to do a circuit simulation, it would be its own network of 4 or 5 different elements, of which the dominant one would be the capacitance, hopefully, because you're buying a capacitor, but you're getting additional things for free that you don't want.
Is it Zener or Schottky diodes that you tend to bias backwards?
Zeners.
Why is that?
Because you want to, I go back to the picture. Remember, diodes have two sides of this equation over here. Usually with a diode, with an LED, we're concerned about this because we want to create a certain voltage and certain current to produce a certain amount of light. But diodes also have this backside right here. And the slope of this line is very steep. It's not vertical because it's not linear. It's a non-linear slope, but it's very, very steep. So if I apply a voltage that is greater than this, more negative than this guy in effect clamps the current. You know,
So it's because the shape is this more sharp turn than forward.
right.
Sharper knee.
It's also
Knee is very
precise.
sharp.
It's a precise
And
distance.
in manufacturing, by where they put that slope, farther out, farther in, on the voltage, axis is how they make the Zener voltages.
Right, you buy a Zener, it's a 6-volt Zener or a 12-volt Zener or whatever.
20
That's
volt
the
Zener,
position of this
100 volt Zener.
trace. And I think somebody else mentioned too the fact that ideally this line would be absolutely vertical so that it would be a hard clamp at a particular voltage. You would know it was exactly 6 volts where it kicked in. Well, that's not really true because there is some deviation in this, so the point at which it kicks in is to a little bit a function of how much current goes through it. So it creates a little bit of inaccuracy as to where that Zener clamps, but it's pretty close.
Exactly related to that, I just wanted to point out one other factor with an LED that can nail you, and that is, like with rectifiers or high voltage Zeners, hooking your 10-volt power supply backwards may be harmless. With LEDs, quite often the maximum safe reverse voltage is relatively low.
Yeah, so just talking about this value right here.
Yeah, that value right there, for a lot of LEDs, is around like 5 volts. And so even though you've got, current limiting, if you hook it up backwards, you can let the smoke out of some of these LEDs at surprisingly low voltages.
That's why the arrow points down. You put it in the trash after it passes that.
Exactly. It's fully consumed. It's fully amortized.
Then I've also seen LEDs used as Zeners, believe it or not.
I mean, an LED is at its root a diode, so it has a function that looks like this. I don't know that I would necessarily recommend it because the Zener is designed to work in that reverse region. It's actually more robust in that capability, but there's no reason to say you couldn't use it. Any diode to do that.
Do surface mounts versus non-surface mounts sing or resonate more? Is that just a function of the dielectric?
In terms of capacitors or what?
With capacitors, yes.
Yeah, I don't know. To be honest with you, I don't know a lot about that. But yeah, apparently capacitors can be subject to mechanical influences. So the changes they can begin to vibrate, which in turn changes the spacing of the conductors and impresses the dielectric, and so they kind of become a dynamic network. And that's as much as I'll say.
Bigger package versus smaller package was more or less susceptible, or the idea?
I don't know.
Why are capacitors used in a circuit? Like, what's their function?
Good question. And I didn't mention this, but I'll mention it now. Thank you. Get back here.
Because reasons.
Because of reasons, obviously. Anybody know what type of circuit this is? Generically? Exactly, what type of filter?
It's a high,
Low pass.
Low pass. And the reason why is, remember I told you the impedance of the capacitor is a function of frequency? So, if I were to plot it, and this is again for an ideal capacitor. Well, actually, I'll talk about that too. So here's a plot of, here's impedance, omega, as a function of frequency. Okay? Now, I didn't really talk about this, but the impedance of an ideal capacitor at very low frequency is pretty much infinite. So it kind of looks like this. That's an ideal capacitor. And that says that it starts off at infinity because, remember, there's two parallel plates with a dielectric. There is no way for DC current to get back and forth. In fact, there's no way really for current, as you think about it, electrons to go from plate to plate. It's kind of a, what's happening is the two plates sit like this, and as one becomes more positive, it draws current out from the bottom to counteract it, or vice versa. So it appears, looking at it, as if there is a current flowing, but there really isn't. It's just, it's an oscillation of carriers at either side of the capacitor, which kind of looks like there actually is a DC current. If that makes any sense. So the impedance of a capacitor at zero at DC is infinite. And we actually kind of showed that here because, if we go back here, if you look at this right here, I start out initially, there appears to be current flowing because there's high frequency energy. I went from 0 to 10 volts, there was a step. So in response to that, the impedance, looking at it from the outside at 10,000 feet, it looks like the impedance of this capacitor is very low, there's a large current. But eventually it stabilizes, it charges up. So at DC, 20 minutes from now, there is no current flowing through there. So the impedance of that capacitor is infinite. Now, because of the math, the impedance of a capacitor is 1 over j omega c. So, right there, the impedance falls off. So at some frequency, in effect, this capacitor should be 0, it should be a short circuit. Now, I'm going to tell you why that's not true, but for the minute, pretend that's true. So I look at the circuit, this is a voltage divider. And what I'm looking at here is I'm saying the V out is the impedance of this lower piece divided by the total impedance. So what happens if I make this impedance lower? Then the numerator gets smaller and smaller and smaller. So the output of V out is reduced. If this were 60 hertz and I'm getting 7 volts, if that were 1,000 hertz or 1,000,000 hertz, this voltage would be diminished because the impedance of this capacitor and this voltage divider decreases. So what happens is if I'm energy coming through and I'm low frequency, the capacitor is high impedance, so I pass unaffected. So the V out follows the V in, which is this right here. If I'm higher frequency energy and I come through the circuit, the impedance of the capacitor is much lower, so a smaller number over a sum is much smaller, so I'm attenuated. It's a low pass filter because it selectively attenuates signal energy. And the higher the frequency, the better attenuation it does. So at some point, if that curve is true, at some point if I increase the frequency higher and higher and higher, eventually absolutely nothing will go out because the voltage here will be 0. Now, I told you this is a lie, and it is. What this actually looks like is this. It goes back up. And the reason being is because parasitics we were talking about before, there's parasitic inductance in that capacitor. And inductance does the opposite of capacitance. Capacitance decreases with frequency, inductance increases. So there's a magic point right about there where these two are equal and it's resonating. But higher frequency, the inductor takes over, the impedance increases. Lower frequency, capacitor takes over. So if I were to build this circuit, that real capacitor, it actually would function as a low-pass filter, and the output as frequency increase would get smaller and smaller and smaller and smaller until some point, past resonance, then the signal of higher energy would start to actually increase.
But that frequency is really pretty high, isn't it?
Depends on the capacitor. It's, and I don't have specifics for you, but the larger value capacitor, if you look at and I'm going to do this in memory, so it may not be totally right. But if you look at a larger value capacitor, say an electric load, starts out here at pretty much infinity, comes down, that's a pretty deep null, resonates, and then starts to go back up again. That's a large capacitor, that's hundreds of microfarads. If I look at a smaller capacitor, say tens of microfarads, it will start up here, it won't have quite the deep a null, but it goes out a little bit farther like this. And so if I continue to do this series of capacitors, they all start somewhere back here, but as the capacitor gets smaller, the frequency response gets wider, but the notch is less. So, to answer your question, is this resonant point so far out that it has no impact? The answer is no. It actually does have an impact. So the way you counteract that in designing a board is you actually incorporate several stages of capacitance, if you will. So the overall system capacitance or system impedance is the vector sum of all of these guys. But yes, this resonant point of capacitor is an issue. And in fact, if you're looking at a board and you're powering something that's very high frequency, like a processor or whatever, putting capacitors on the board, even small surface mount capacitors right up against the ASICs, at some point really have no impact because you're out beyond the resonant frequency. You're out here somewhere in the right-hand weeds. So they have to get exotic, and they have to place the capacitance closer and closer and closer in toward the ASIC, so they're fabricating in part of the part. And the other thing they do is, remember, most boards are multi-layers, right? So you have the best thing to do in a high-performance board is to put a power layer and a reference layer, not ground, adjacent. And then you have a signal layer where you've got some signal traces up here and some signal traces up here, and then you have another sandwich. The beauty of this is, what is a capacitor? A capacitor is two conductors placed closely together. Well, it's very difficult to get two pieces of metal closer than that. I mean, this is it's a relatively large pair of metal conductors placed pretty darn closely together. They're only a few thousandths of an inch apart. This becomes a capacitor. And this actually is the best capacitor on the board. This is your best high-frequency capacitance. And it's not because of a capacitor placed on the board, it's an intrinsic function of the geometry of the board. So yes, capacitance absolutely makes a difference. And this idea that capacitor just goes out like that is not true. And the faster you go, the farther you get out to the right, the more you realize that's true. Cool. Anything else?
So you're filtering more than 60 hertz. Is that what I heard? Is that the
Well,
point?
what you would do is you got to figure out, I mean, this is an artificial thing, right? Pretend this was not just a power supply. This was an input from something else. It was a signal that was coming from some circuitry over here. So I have to think about, okay, what frequency stuff do I care about? You know, am I communicating at 10 hertz and therefore I'm well below 60 hertz and its harmonics? Or am I communicating at megahertz, so I'm well above the 60 hertz and its harmonics? So I got to kind of figure, I got to look at the spectrum and say, what do I care about? I want to get what I care about through successfully. And then I want to look at, so what's this other junk? And is it how high is it? Is it very, very small and therefore I don't care? Is it significant relative to the size of the signal I care about? Well, then I care and I need to take action to diminish that frequency. And so I can get fancy. I mean, this is a low-pass filter. This says basically everything that's low is good, everything that's high is bad. You can make high-pass filters. So you're basically saying everything that's high is good, what's low is bad. You can make notches. So you say, I like the low, I like the high, I just don't like this area because I need to get rid of this energy because I'm doing something here. So you can tailor this. This is the simplest filter probably. But yeah. So it's the key about something like this is you look at signals. People look at signals like this. Here's a clock, right? And we know tonight that this doesn't exist, right? It actually looks like this. And the effect is more pronounced as you go faster. But what's the frequency content of that? I mean, let's say the clock's 100 meg. Does that mean the frequency of this clock is just 100 meg? No. It's probably a square wave since it's a clock. So Fourier says to make a square wave, you have to have a fundamental and an infinite series of odd harmonics. So you have to have the first, the third, 3x, 5x, 7x, 9x, 11x, 13x, 15x, through infinity. So the actual frequency content of the signal begins about 100 meg and goes up to what they call knee frequency. The point, eventually the harmonics just diminish because you just can't have harmonics going on forever because nobody can make a 500 gigahertz signal or whatever. So the amplitude of the harmonics begin to diminish. There's like a low pass function going on. But there's still some wide bandwidth that you care about. This signal has significant energy from about 100 meg, probably up to a few gig, like 2 or 3 gig. So now you say, okay, well, do I care about that? Well, let me think. 2 gig's pretty damn fast. And 2 gig has a bandwidth, or a wavelength that's pretty small. So as my wavelength gets smaller, more and more things look like antennas. I get closer and closer to RF space. So now I'm like, I got all this energy spewing inside my box from 500 meg to 2 gig. If it encounters any type of structure in the box that looks like an antenna, boom, I'm blasting it out into space. And EMC guys get really upset. So this is not, to say this is, well, this is just 100 meg. Doesn't encompass the whole thing. This is a package, an envelope of energy that goes from X to Y. So yeah, you have to frequency manage. You have to say, where am I spewing and what's good with that or bad with that, and then who else is trying to get me? I mean, if I'm doing my stuff and I'm fat and happy and you build a radio transmitter next to me and blast this high frequency into my circuits, I'm going to be upset. And, you know, that's EMC is like
lawsuit.
EMC means I don't come out there and mess you up, and it means you don't get to come over here and mess me up. So we need to stay apart. So you have to manage frequency stuff.
That's what shielding is for.
Or keeping your fingers crossed, or just a crap load of ferrite beads and copper tape. But
Or just keep telling them, part 15, part 15, this thing is part 15, which means you have to accept.
Yeah, that's the other part of EMC. It's not just I'm not allowed to mess you up. It's I'm supposed to be able to take a certain amount of interference from you.
right. Yeah, you have to be. But
In one of your slides, you have the capacitor is J times 1 over omega C, and in another one, you've got the J on the bottom.
well, I'll show you, and it may be an error, but let me show you something. J. He's a weird guy.
It's just imaginary anyhow, right?
If I say, sorry about this.
Oh, I see it. So it's J squared over J. It's minus 1.
Exactly. So when I'm squaring this, you're right. I'm moving this guy around. I can move this up to the numerator and make him a minus J. Minus J in the numerator is equivalent to a positive J in the denominator, vice versa. It's J magic. Now, that's not to say I didn't screw up the algebra. I won't say that, but. I had, when I was in school 100 years ago, I was taking an engineering class and a math class simultaneously. And I think the engineering doc liked J, and the math doc liked I. And I really preferred the math doc's presentation. I just think he did a better job explaining it. So I took his notation, and I took it's like a midterm exam in the engineering class, and everything was I. So I got a 0 on that test. And Dr. Wang, the engineering professor, was a very brilliant man in his own right, but spoke very little English. I mean, Chinese was his first and second language. So I went to Dr. Wang and I said, Dr. Wang, I said, I'm confused. I think this is correct. I've done the work twice. I showed it to your TA. He agrees that it's right. Oh, no. You have too many I's. What is I's? Should be J. And I'm like, no, sir, I think they're equivalent. It's like the reluctance and the negative capacitance. It's like, it's just nomenclature. I'll never forget that. What are these I's? Thank you, Kevin.